Now our last speaker of this workshop will be Joanna Luc. She will be talking about indeterminism in general relativity, spurious and non-spurious. Please, Joanna.
Okay. I would like to thank the organizers for inviting me to this conference. My topic will be spurious and non-spurious instances of indeterminism in GR, and I will actually start with a spurious one, which arises in the whole argument, but I will claim that there is an interesting argument to be had that they are indeed spurious, which is in contrast to some recent literature according to which the whole argument arises out of making some basic mistake in using the mathematical formalism of GR. And then, using some of the insights we will gain during the discussion of the whole argument, I will discuss a candidate for a non-spurious witness of indeterminism in GR, which are non-isometric extensions of Taubman spacetime. And the last part will be about quite different kind of witnesses of indeterminism that we might find, which are non-Hausdorff manifolds. And the difference here is that the witness is now a single GR model, not a pair of models. And this talk is based on 3 papers of mine, one of which is co-authored by Tomasz Placek. So let me start with reviewing the whole argument as it was formulated by Ehrman and Norton. Some of those details will be needed for my later polemics with Wetherall and Halvorsen and Manchak, which is why I present those formal details. For them, the whole argument concerns not just GR but all local spacetime theories which have models of this form, where M is a differential manifold, OI are fields of geometric objects, and the last n minus k plus 1 of those objects are actually the left-hand sides of the dynamical equations, and they need to be tensor fields. So the equations look like this. Those fields from OK to OA, n equal to 0. And according to Ehrman and Norton, the whole argument consists of these 2 steps. The first is Gauge theorem, which says that if we have a model of local spacetime theory M and we take any diffeomorphism, then the model obtained from the new model obtained from the old one, but by taking the same manifold and pushing forward all the geometric objects field, is also a model of the same theory, and from that they derive a conclusion of radical indeterminism of theory T. So again, some more details. As I said, like the dynamical equations are those last objects in the model equal to 0. They can be written in the coordinate form, this equation 2. And then let us consider, let us first transform those objects by means of a diffeomorphism. Then the trick is that we could also transform the coordinate system, which is equation 3, and we can observe that we transform both the objects, which is an active transformation, and at the same time coordinates, which is a passive transformation. Then like those the result of those transformations cancel out, so that the coordinate expression for those old objects in old coordinates are the same as for the new objects in new coordinates. And by combining 2 and 4, we can conclude that those new coordinate expressions are equal to 0, but we know that those objects are tensors, so if they are equal to 0 in one coordinate frame, then they are equal to 0 in their components are equal to 0 in any other coordinate frame, in particular the old one. So the new objects in old coordinate frame have also components equal to 0, so we can like move again to coordinate free formulation, and we have obtained equation 7, which shows that these are the objects in the new model satisfy the same equations. There will be some more details about that in what follows, but this is where Ehrman and Norton end. So now let us consider a particular diffeomorphism, the so-called whole diffeomorphism. We choose a bounded region H of M, and we consider the following diffeomorphism. It acts as the identity outside of the whole H, and it differs from the identity inside. Since this is a diffeomorphism, the new model obtained by using this diffeomorphism is the model of the same theory by the gauge theorem. But then we can observe, Ehrman and Norton observe that this diffeomorphism is special. It acts as the identity outside of some chosen region, which could be arbitrarily small, which means that fixing the values of OA of O1 to ON outside of the whole is not sufficient for fixing the values of those fields inside. And this behavior Ehrman and Norton call radical local indeterminism. It is radical because fixing the values of the quantities on arbitrarily large part of the manifold is not sufficient for fixing the values within the whole. And I will use I will elaborate more on how to understand that indeterminism being radical, and this will be somehow important for me, that this is not just indeterminism but radical indeterminism. So this seems to be a problematic feature of a theory, that we encounter such radical indeterminism, but there is, Ehrman and Norton claim, a simple solution to that, namely we should regard as physically equivalent those models of a theory that are related by a diffeomorphism, which means not only that there is a diffeomorphism between their base manifolds, but also that this diffeomorphism, by pushing forward the original objects, we obtain the objects from the new manifold. And they don't stop there. They also argue that this argument counts against substantivalism with respect to spacetime, because they claim that substantivalist is committed to rejecting Leibniz equivalence. I will not talk about that part of the debate, so I'm interested really only in that physical equivalence issue. So now why do some people say that the whole argument is relies on some basic mistake? Or one of those people is Wetherall, who says that this argument seems to rely on a kind of equivocation, in the sense that we use at the same time different standards of comparison of models. When we say that the models are physically equivalent, we use isometry as a as a standard of equivalence, and when we say that there is radical indeterminism, which requires the models being different, we use another standard of equivalence, which is another standard of comparison, which is the identity. So this kind of equivocation of or double standard of comparison is bad. So this I take to be one part of the argument, and in the other part, perhaps even more important, is that we actually do know what is the correct standard of comparison, and Wetherall thinks we can extract that standard from the scientific practice. So the scientific practice with respect to GR is such that the standard of first the models of GR are Lorentzian manifolds, and the standard of comparison for Lorentzian manifolds is isometry. So we should just use that standard throughout in any context when we compare two models of GR. So we can't make that claim that some radical indeterminism or even just indeterminism arises. Another paper which points in a similar direction is more recent by Halvorson and Manchak, and they say that the whole argument has three main ingredients: the assumption of some antivalues, which is something I don't discuss, certain mathematical facts that are supposed to underlie the conclusion, and like that issue of pernicious or radical indeterminism, and then they claim that there are actually no mathematical facts to support the whole argument. They think there are two candidates for such facts. One is that they're distinct by isomorphic models, and they think Wetherall killed this root of the argument, and the other option is that there are isomorphisms that only move elements inside a hole, and they claim that none of the candidates for the isomorphisms of GR models can be used in that argument, and this is why, and this is because there are maybe I should first say what they mean by moving elements inside a hole, which is related to their definition of indeterminism. But in short, their strategy is first to show that the notion of isomorphism is involved in the whole argument, and actually in the both steps that I distinguished, and then that no plausible candidate for the notion of isomorphism can play the required role in the argument. And later my strategy will be to show that the notion of isomorphism is not needed at all for the whole argument to work. And so in the step one, they claim the notion of isomorphism is used to establish that the old model and the new model are indeed models of the same theory. And more interesting is the second step, and for that they propose a particular definition of indeterminism, which I will complain about a bit later. So they claim that a theory counts as indeterministic if there are two models such that two models with like base manifold and some object fields on it, such that there is a proper open subset of M, which is small enough so that the rest of M contains some initial segment, and an isomorphism that changes things in O but not outside O. And what it means that it changes things in O but doesn't outside O. Well, they propose that this should be captured in terms of another isomorphism. So in the end, their proposed definition is that these two models would count as a witness of indeterminism if there are two isomorphisms between them which agree outside O but disagree inside O. Yeah, so here is my answer to that. First, regarding step one, does it really rely on the notion of an isomorphism? I claim it doesn't. I have shown you the argument by Ehrman and Norton, and it didn't appeal to the notion of isomorphism. Instead, what they were showing is that the new model satisfies the same dynamical equations as the old model. But then there comes the question, what does it mean that they satisfy the same dynamical equations? And here I think there is some little work to do. We need to add some more details to Ehrman and Norton's argument to make it work. If the same dynamical equations means that the left-hand sides of those equations are isomorphic tensors, then we are back to the Manchak's and Halvorson's line of argument, because we use the concept of isomorphism to spell that out. But I think there is a different understanding which relies on the notion of the functional form of the equation. So maybe it's good to explain that by contrasting two facts, which one of which is trivial, the other isn't. So we know that in Einstein's equations there is the Einstein tensor, which depends on the metric and its derivatives. And of course, if in that expression for the Einstein tensor we replace the metric by some other primed metric, then we obtain expression of the same form. This is trivial and uninteresting. What is non-trivial is that if we if we apply diffeomorphism to that object as a whole, then what we obtain has the same functional form in the sense that it depends on the transformed metric in the same way as in the same functional way as it previously did depend on just GAB. And more generally, this I propose to be the schematic expression specifying what it means that the functional form of an expression is preserved, and it is a non-trivial fact that the equations of TR are so that that form is indeed preserved under diffeomorphisms. So what I suggest to add to Ehrman and Norton's argument to make it work under that explicitly dynamical reading. So first of all, well, perhaps they had that implicitly in their minds while writing, but this is not explicitly in their paper. So I'm just making that explicit. So first, those objects that are the left, you remember, like in their proposed form or form of the models, the last n minus k plus 1 objects were the left-hand sides of the dynamical equations, and they should be first they should be the functions of the other objects and their derivatives, and as such functions they should be form invariant under diffeomorphisms. And we should also say that two models are models of the same theory if they have like the same number and the same types of geometric objects, and and their dynamical equations have the same form. So regarding step 2, I will say more about the problems with the definition of indeterminism proposed by Halvorson and Manchak later. So for now, let us forget about it and think from the scratch what indeterminism is and how could it be defined. A general idea is that two models of some theory are a witness of indeterminism of that theory if and only if they agree on some sufficiently large region but disagree elsewhere. So this is of course schematic and to be made precise. So first, what is that sufficiently large region? And like if we look at the technical literature on GR, then there is a good candidate which are Cauchy surfaces, and there are theorems that if we fix the initial data on Cauchy surfaces, then for a certain and some other conditions are satisfied. In particular, we restrict to globally hyperbolic models, then the evolution is unique, so we have a determinism. But this definition makes sense only for globally hyperbolic models, which form a proper subclass of all models of GR. And moreover, some like interesting candidates for witnesses of indeterminism lie outside of this class. So it's interesting to consider some other definitions, and motivated by that, one can propose that perhaps we shouldn't fix that kind of sufficiently region in advance, treat this as a parameter of a family of different definitions of indeterminism, and this is what Butterfield and Dobrzewski propose. But actually, in the context I'm interested in, which is the whole argument, we don't need to decide, and this is because here we have not just indeterminism, but radical indeterminism. So no matter how large are those sufficiently large regions, there still would be instances of radical indeterminism because the holes could be chosen to be arbitrarily small. And what it means that they agree or disagree. So here my proposal, which is contrary to Wetherall, is that we shouldn't decide in advance what is like the kind of maps that should serve as a standard of comparison of models, but rather we should consider different definitions of radical indeterminism which are relativized to the choice of that kind of map. And we should investigate what are the consequences of various such choices. Another thing is that we actually don't need like the full definition of radical indeterminism, but to proceed with the whole argument, partial definition suffices. So here is what I propose. This is partial definition of radical indeterminism relative to the kind of maps K. So if a theory has a model M such that there is an infinite series of regions Hi, which are those holes, and condition 1 says that they can be taken to be arbitrarily small, and condition 2 says that for any such hole there is some other model of the same theory such that there is a map of kind K there is a map between these models such that this map restricted to M without the hole is of kind K, but there is no map of kind K between these models taken as holes. If this is satisfied, then we can say that T is radically indeterministic relative to K. What would the whole argument look like? I want to suggest that the whole argument can be understood as being based on this definition relativized to K being the full identity, whereby the full identity, I mean that first it transforms every P into itself, any element of the manifold, and the values of all the geometric objects at any of these points agree. So now, and I want to present this as the whole argument understood in this way. I want to present as an instance of a more general strategy for formulating interpretations of physical theories, which is iterative in nature and relies on a kind of reflective equilibrium idea. So in the case of the whole argument, we just take tentatively the full identity to be the standard of comparison of models. We investigate the consequences of that, and we realize that, oh no, that relative to this choice of maps, this theory is radically indeterministic, so we should choose a different kind of maps as our standard of comparison, provided that there are no there are no obstacles for that adjustment. And what could be a possible obstacle? Well, if, for example, we choose some other kind of maps K, and it turns out that there are some models related by K that are actually empirically distinguishable. In that case, we shouldn't choose K. Or perhaps in such an imagined situation, if we have to choose between radical indeterminism and identifying empirically distinguishable models, perhaps we should just choose radical indeterminism. So it's a matter of weighting different advantages and disadvantages of a given choice of maps. So here are my responses. First, to Wetherell, I think that his were appealed to scientific practice to establish the standard of comparison of models is kind of unilluminating. There should be some substantial argument that this is a good choice, and I think that the whole argument under the reading I've given that's a good argument for Leibniz equivalence. And we don't need to decide in advance what is the standard of comparison. We can choose one tentatively and investigate the consequences of that choice. And my reply to Halvorsen and Manchak is that the whole argument doesn't rely on the concept of isomorphism, but on the homomorphism invariance of dynamical equations. Their claim that no choice of isomorphism for GR models could support the whole argument is kind of irrelevant for the whole argument under this reading. And instead of their proposed definition of indeterminism to be used in the whole argument, I suggested we could use partial definition of radical indeterminism. But in the end, I agree with them that that instance of the indeterminism that arises in the whole argument is not genuine, and that the homomorphic models are physically equivalent. So on that we agree, but we disagree on how to reach that conclusion. Yeah, so now about some non-spurious witnesses, or at least candidates for. So I will be very schematic here. One of the solutions of GR is the so-called taupe spacetime, which is maximal globally hyperbolic. But if we consider also solutions that are not globally hyperbolic, then among them there are extensions of taupe spacetime. First, we can extend them. Maybe one important detail. That here, this temporal part is finite, and we can extend those solutions upwards and downwards, and from those we can also obtain the solutions that are infinite in both ways in the temporal variable. And it turns out that there are 4 such extensions, and some of them are isometric and some others aren't. In particular, these 2 aren't, and this might be a good candidate for a witness of indeterminism of GR. And another interesting thing is that we can proceed, continue that construction, and we can actually glue together some of those extensions and obtaining in this way non-Hausdorff manifolds. So what should we think about those non-isometric extensions of taupe knot? It is a matter of discussion, but I suggest that we should say that they are instances of indeterminism, but not radical indeterminism. And if we define determinism, indeterminism in terms of Cauchy surfaces, then we wouldn't capture that just because it's applicable only to a globally hyperbolic case. What about the definition by Halvorsen and Manchak? Well, it actually also it presupposes that for 2, according to them, when 2 manifolds, 2 models are an instance of indeterminism, well, there should be 2 isomorphisms between them, and they should kind of partially agree, partially disagree. But this means that there should be an isomorphism between these 2 models in the first place. But this is not what we have in that, I think, more genuine candidate for a witness of the indeterminism, where we have the models that are not isometric, so they are not isomorphic in the relevant sense. So in the light of in light of that definition, they would count as kind of incomparable, I would say. This definition doesn't seem them as being an instance of indeterminism, but this, I think, is incorrect. And the problem is that we postulated that there must be an isomorphism between the models in the first place, whereas indeterminism means that somewhere the models differ, which means that they are partially non-isomorphic and partially isomorphic. Yeah. So what about my definition of a radical indeterminism? Well, here, relative to isometry, here this condition is violated because there is no isometry between them, so they don't count as being an instance of radical indeterminism, which I think is good because this is just a usual indeterminism, not some bug in the theory that should be removed by its reinterpretation, but a real instance of indeterminism if we allow models that are not globally hyperbolic in the first place. Yeah, and if we consider that flexible definition with different possible choices of the kind of sufficiently large region, then this is in the paper of Juliusz Dybszewski. He argues there that if for that kind of region we choose maximal globally hyperbolic part, then those non-isometric extensions of Taubnat would count as an instance of indeterminism. And now the last part of my talk, which is about non-Hausdorff manifolds that arguably form a different kind of witnesses of indeterminism. So to recall, Hausdorff condition is a topological condition according to which any two points can be separated by open sets, in the sense that there are two open sets such that one point belongs to one, the other to the other, and they overlap emptily. And this sounds like a very abstract condition, but actually has some physically interesting consequences. One is that any non-Hausdorff manifold either is not strongly causal or admits bifurcating curves of the second kind, where the second kind means that, a bifurcating curve is a pair of curves, and of the second kind means that there is the first point of which these curves differ, and they are important because such curves could be also geodesics. So in such manifolds we could have bifurcating geodesics. And another interesting feature is that manifolds that are non-Hausdorff and possess those bifurcating curves of the second kind, they might fail to have a maximal extension. So these are physically interesting consequences of the violation of the Hausdorff condition. And in one of my papers, I kind of defend the legitimacy of those objects. I argue that they could be legitimately regarded as models of GR, and there I use a functional criterion. So I claim that the function that the kind of what I call there the basic object of GR is supposed to play is that it enables one to pose the equations of evolution for some matter, and it turns out that non-Hausdorff manifolds are good enough in the sense of supporting enough differential geometry so that they are able to play that role. And another point that I make is that well, I consider some objections against the physical reasonability of such models, and I argue that they are not as decisive as it might seem, judging from the fact that the Hausdorff condition is often regarded as a part of a definition of differential manifold. So in particular, well, in that argumentation, I use the modal interpretation of those non-Hausdorff manifolds, which I will describe in a moment. But with regard to that possible violation of strong causality, about that I say that okay, this sometimes is strong causality is sometimes regarded as one of the physical reasonability conditions, but what does it mean exactly? It means that there are no, so to say, almost closed time-like loops. But the really strong arguments for the problematicity of such loops concern exactly closed time-like loops, which are suspicious because they might lead to some paradoxes, or at least have some potential for leading to some paradoxes, such as the grandfather paradox. But like, we don't have equally strong arguments against almost closed time-like loops. And there are people making those arguments, but they rely on kind of fine-tuning reasoning. So they say, like, if we have almost closed time-like loops, then we are kind of close to accepting exactly closed time-like loops, which would you know, like a small quantum fluctuation could lead from almost closed to exactly closed. So we should better disregard all of those, but this requires some further substantial assumptions to conclude that we should forbid not only exactly closed time-like loops, but also almost closed. And now about that modal interpretation, it relies on the theorem given by me and Tomasz Placek, which states that any non-Hausdorff manifold can be obtained by gluing together two or more Hausdorff manifolds. So, for example, we can glue together those non-isometric extensions of Taubnat spacetime and obtain in this way a non-Hausdorff manifold. And this can be used as the underpinning of the modal interpretation of those structures, because then we can view those maximal Hausdorff submanifolds as representing possible spacetimes, and the entire non-Hausdorff manifold as representing a bundle of possible alternative spacetimes. And this, I think, is interesting because then, in contrast to our previous cases that I discussed, a witness of indeterminism is not a pair of models or a class of models, but just a single model. We use that to undermine some of the objections against non-Hausdorff manifolds, for example, those bifurcating curves, which are bifurcating geodesics, could be interpreted as like possible paths that a particle could take. But there is actually one subtlety here, namely, it turns out that it's actually not so easy to have those bifurcating geodesics, which, if we subscribe to that modal interpretation, they are actually quite welcome, because they mean that it's not only there are not only different possibilities for space-time to evolve, but also for like point-like objects. But, and this will be the last thing, but it turns out that if in that gluing procedure by which we obtain a non-Hausdorff manifold, if that gluing is maximal in the sense that it cannot be extended in a continuous way, then there are no bifurcating geodesics. Okay, so to sum up, I agree with most of the literature that indeterminism that appears in the whole argument is in the end spurious, but I think there is an interesting argument to be had for that claim, and this is actually the whole argument itself, but I added some more details to defend it from various objections. And like that broader context is that I see the whole argument as being an instance of an iterative reasoning which could be used in the interpretation of various other physical theories, or maybe scientific theories in general. The second point, that there are some good candidates for non-spurious witnesses of indeterminism in GR, such as non-isometric extensions of Taubnat space-time, but not all proposed definitions of indeterminism classify them correctly. And the last point was that we could have also witnesses of indeterminism in GR in a different form, namely in the form of a single non-Hausdorff manifold. And that's all. Thank you.
Niels Lennemann will comment, please.
Oops. Yeah, thanks a lot, Joanna. Very intriguing, very interesting discussion on determinism in GR, and kind of a tour de force via whole argument, top lab space, and then finally to your branching space-time work. Very simply, just one kind of perhaps even stupid question and one kind of constructive proposal with respect to the branching spacetimes. Let's start with the clarificatory question. I kind of trouble to see why there's not a sense in which it makes sense to talk about isomorphism. Why not even in your no isomorphism approach there is ultimately an isomorphism? I mean, you say the whole argument does not rely on the concept of isomorphism, but on diffeomorphism invariants and dynamic equations. My question really is a disagreement with Habers and Manchek, and maybe also with Westerwald, not really about what kind of isomorphism is at play here. I mean, okay, the reconstruction, as you said, of the whole argument is in terms of subtotalism, some mathematical effects, and some form of indeterminism. Let's jump to the mathematical effect. So they claim there's this isomorphism of some form between two spacetimes, x and y, which changes things on a certain hole O, but nowhere else. Then they kind of give finer placeholder versions of this, right? Where they introduce, in addition to this kind of naive isomorphism, phi, which is supposed to change things, another isomorphism, which is supposed to capture a standard of comparison. Let's call it psi, right? So you have different variants of this. I think the details are not so important unless people want to hear about them, but I think we just skip this for a moment. And so you can flesh out what you mean by phi and psi differently. This is Neil Dewar's reconstruction. So according to Neil Dewar, Havels and Manchak would fill in phi and psi with isometries. The isometries is defined in a certain way, it's kind of standard. And Ehrman and Norton, according to Dewar, not quite right, it needs to be said, fills in phi and psi with isometry and diffeomorphism respectively. And I see you to come along and say basically, yeah, more or less, but actually Dewar is after you, he should really have read you properly. Phi is an isomorphism in the sense of diffeomorphism in the narrow sense, so diffeomorphism plus drag along of the geometric objects. And psi is an isomorphism in the sense of a diffeomorphism in general. Whether you set the psi to 1 or not, I think it depends a bit on the context. Maybe you want to say not. Maybe also your what you call, so to speak, phi and psi is the other way around. We might have to talk about this, but in any case, it seems to me you're basically fitting well into the scheme here. And one point you really stress is that this holds because we have diffeomorphism invariance of the theory, just like Manuel Reed. So yeah, I just want to ask, don't you after all provide an isomorphism with a narrow diffeomorphism invariance that preserves solutionhood? And what is really the point of saying you do it without isomorphism? So, sorry, this is really maybe stupid, I didn't say something, but yeah, maybe we start with this first question.
Okay, good. But I want to have my slides again, sorry. Yeah, so one thing is that, okay, it might in the end turn out that the correct standard of comparison of models coincide with their mathematical isomorphisms, but it doesn't need to be the case, and actually Wedera has Wedera considers modified GR models, which are like standard Lorentzian manifolds, but on the top of that they add what they call the individuating field, which is just labeling every point of the manifold. And those new objects have different isomorphisms, but I would say if we think about them as models of GR, then still diffeomorphism related models should be regarded as physically equivalent, which means that in this case that physical equivalence and the correct standard of comparison of models doesn't coincide with isomorphisms. So this is one thing, and another thing is that I have I don't think I fit into the scheme of Halvorsen and Marchak. I think I think that the scheme itself is wrong, and this is because because it doesn't capture correctly that non-spurious example, right? Because for two models to be witness of indeterminism, according to their definition, there must exist an isomorphism between them, right? And I would say, no, like the genuine instances of indeterminism is where they do differ, right? And in the case of non-isometric extensions of Taubnat, we have the situation that there is an isometry between their proper parts, and there is no isometry between models taken as wholes, right? Which fits into that, which fits into that scheme that I had here, right? That indeterminism is when they agree on some sufficiently large region.
Right.
They agree on that tau part, which is maximal globally hyperbolic, but they disagree elsewhere. And my partial definition of radical indeterminism also fits into that scheme in the sense that I say we have radical indeterminism when there is a map of kind K between, well, here it's not, we don't have a fixed kind of sufficiently large regions, but this is because this is radical indeterminism, so it should work for any kind of regions. There is a map of kind K between like sufficiently large proper part of models, but there is no map of kind K between models taken as wholes. Of course, like for any choice of the whole, we will have a different model M prime, right? So here, like an instance of usual indeterminism is just a pair of models. An instance of radical indeterminism is a family of models which has like one original model here, and for any choice of a whole there is some other model which is such that it is K related. Its proper part is K related. That's, well, not arbitrary proper part, but just the entire manifold without the whole. But that model as a whole is not K related to the original model.
Right, but would it be fair to say that, say, Menon and Reed fit into the previous scheme I showed? I mean, they don't have this this kind of iterative procedure you described. I mean, they construct something. They define something called a whole isometry, so to speak, the standard as their phi, right? And I really don't see why this wouldn't be captured by the.
I'm not sure about Menon and Reed.
Okay,
perhaps they just didn't address that aspect. They focus on that part of the whole argument being dynamical, which is what I also stress, but I don't know what would they say.
They can capture its dynamic. Oh, sorry, maybe we go back to the second moment. So let's say this here, in a sense, also I think can capture its dynamical. I mean, depending on what kind of geometric objects you're dragging along, right? And I think this is a fair reconstruction of Menon and Reed, and at least.
Okay, maybe I don't know, but I just don't have those two global isomorphisms. Right?
Okay, but it's not of you. Okay.
Yeah.
Okay, and again, in that sense, so to speak, yes, you don't want to talk about this. Okay, you just it says there exists no K for them. Good, fair enough. Okay, this helps. And then we come to part 2. I really also like your work on branching spacetimes. You already, I think, sketched a bit how you can defend branching spacetimes as somehow physically reasonable GR models. There are all kind of problems you could think naively. I mean, raised, for instance, by Ehrman, some kind of goes against some kind of presupposed determinism. I think this is probably a bad reason against it. Energy conservation issues, problem that you don't have maximally extended spacetimes, and fair enough. My comment is just, in any case, I find them pretty useful as this branching spacetime as modeling tools, so to speak. If you go beyond GR, would you be happy with this? I mean, one example would be, for instance, to model branching spacetimes or position of spacetimes in the context of Indeterminism, shield axiomatization. We worked a bit on this, and I was wondering what you think of this. Maybe you have some statement on that. Whether it's kind of taking this in a wrong direction, or whether you're actually happy with saying this is the right way of using these models as far as usable, because you don't really expect them to model actual classical spacetimes after all.
Okay, so one terminological thing. It seems to me that this expression branching spacetime is used in a bit ambiguous way. So meaning of that is as a name of a separate axiomatic theory, which is summarized in a recent book by Belknap, Miller, and Placek. And this is just a separate theory that tries to connect indeterminism understood generally on the one hand with like some features of relativistic spacetime, but not all of them, like mainly the causal order, right? Mm-hmm. So this is one meaning of branching spacetime, but another meaning is like more loose, I would say, is where you encounter in some other theory like some branching structures, which might also be actually models of that theory. So these two are connected, but I wanted to stress that difference. So what I discuss is more branching in that second sense, where in GR we encounter models that have those branching features. And like the motivation for the theory of branching spacetimes was actually that on the one hand we have some reasons to believe in determinism, and those might come from considering human agency, but if we consider physics, then they come mainly from quantum mechanics, which means that it is of course natural to look for such structures wherever we try to connect relativistic theories with quantum theories. So I of course agree that this is a good usage of that approach and a good place to look for that branching behavior.
But could you think of other uses, so to speak, just within GR, just in the classical regime?
No, like I see no reason to restrict the classical regime.
But could you actually see use within, so to speak?
You mean other than some toy models?
Yeah.
Well, I'm not sure, but well, if for example you believe in some indeterministic interpretation of quantum mechanics, such as GRW, then you can perhaps represent like at least some systems as being to a good approximation described by like some relativistic spacetime, perhaps even Minkowski, together with that GRW or similar dynamics, and that would, if you wish, that could also be captured by those kinds of branching structures. And this actually relates to one of Ehrman's objections, because he was complaining about there being like no account of why this branches in this way and not some other way. So one source of branching, so to say, could be just the dynamics of matter, which is indeterministic, but by the very nature of indeterminism, it follows that the theory doesn't settle what exactly will actualize. So, and I think Ehrman was still somehow not satisfied with that remaining degree of arbitrariness, but that seems to be that seems to lie in the very nature of indeterminism. Thank you.
I have a question. Just coming back to what you said at the very end, I don't quite see how that's supposed to be working, because as I see it, GRW can be implemented, in a form that violates relativity, I suppose, in Minkowski spacetime. Or if you want to make it relativistic, you can introduce the flashes or do something like that. But how is branching supposed to be helping? Because it's a splitting of the world rather than a duplication of the world with two alternate futures in a way. So I don't quite see how that's an interesting, useful form of indeterminism that's capturing what we think the indeterminism of, say, quantum physics is.
So I wouldn't say that we are forced to use those branching structures. They are rather an alternative way of representing indeterminism, which differs, for example, from Luis's possible worlds approach, in that we don't have like a separate non-overlapping possible worlds, but we consider them as partially overlapping and at those indeterministic moments as branching. And those structures can be interpreted in various ways. So one can give to that a kind of multiverse interpretation, according to which all those branches are on a par. But actually, the creators of branching spacetime theory, and also me and Tomasz in the papers that I mentioned, we all were working with an interpretation according to which out of those various possible evolutions, only one actualizes. So the branching structure as a whole does represent not only the actually realized universe, but like the whole bunch of possibilities out of which only one is realized.
Okay. But what I don't understand is that, you can easily see how the branching structure works and how it sort of, all of a sudden there's like a rip in all space-time with two sort of future parts, but it's not like these are like copies which are almost the same but just differ in that, the measurement is up in this branch and down in the other branch, but it's really like a rip across the world. The Western hemisphere is in one, the Eastern hemisphere in the other world, and we can never communicate anymore.
Yes, so it doesn't need to be like this in the sense that, so to say that branching division could propagate along the causal lines, and this is like those kinds of models are considered in the book about branching spacetimes that are mentioned. So it doesn't need to be that you assume that you have some fixed slicing and that branching happens along that cut given by that slicing. It might respect the causal structure. Okay, so you kind of you glue together two spacetimes along the lines, determined by the light cones. Okay.
So that you would have in the future in the branches two almost identical copies of the world as it was before.
Well, whether they will be almost identical or not, that depends on the details. So if we imagine well, it depends. It could be almost identical, but there is no reason for this to be. So if we are considering like the contents of the spacetime, but perhaps what you meant is that kind of the spacetime part itself is almost identical, right? Because of that respecting causal structure. Is that what you meant?
That's part of what I meant, for sure, yeah.
Okay. Yeah, so in that sense, they often will be almost identical, but again, they might have, for example, different metrics, as in this case of gluing together non-isometric extensions of Taubnat. So they could also differ in that spatio-temporal part, not only in that matter part, so to say.
Okay. Thank you. Nick.
So thank you. So there was great stuff there, and especially some of the weirder spacetimes. That's very interesting. So I'm a bit worried about coming across as like the old guy who's seen it all before, kind of. I don't want to sort of say that, but maybe that's, yeah, okay, if you feel that, it's okay. So back in the 80s and 90s, right, when the whole argument came out. Sorry?
But that was boring.
So these things were, but one of the focuses was clearly about how these different models and whether they are different actually represented the world. Part of the discussion, and that's sort of built into the different forms of substantivalism, sort of manifold substantivalism or sophisticated substantivalism. How does that, so in the way that you sort of presented it, it's not on the face, it's not sort of, it seems to be made explicit where the views about how these models represent come in. I assume it's sort of in there, otherwise I just don't see how, right, that there could be a kind of worry about indeterminism unless that's there, just sort of, if it's just sort of purely mathematics. I don't quite, it's about how the world is, so there has to be, it seems to me, a representational part. So, yeah. Does that make sense? And can you sort of comment a bit about, I mean, in a way maybe it's like trying to latch this on to how I, grew up thinking about this stuff.
Okay, so I'm not sure if I understood of your question, but I will try to address that. So, as I said, I don't delve into that substantivalism versus relationalism debate. I'm in that paper and in this talk, I'm only concerned with that issue of physical equivalence of models and whether physical equivalence of diffeomorphism-related models is compatible with substantivalism or only with relationalism. I didn't discuss that, although I'm quite convinced that some more sophisticated forms of substantivalism can accommodate Leibniz equivalence. Yeah, another point, you have that worry that this is too formal and doesn't take into account those representational aspects. And indeed, in what I discussed, perhaps they weren't very explicitly present, but the general idea is that the whole argument is an instance of iterative reasoning, which consists of like taking some interpretational proposal, including in this case a kind of maps that serves as a standard of comparison, and as such also as a proposal for the standard of physical equivalence of models. And once we make this tentative choice, we investigate its consequences. And one of those might be that under this choice a theory is radically indeterministic. But this is not the only issue to be considered, right? I mentioned briefly that what is important is also empirical equivalence of models. And there might be other issue to consider, and we should take all of them into account when deciding whether, for example, a given choice of the standard of comparison of models is the right one or isn't. And it might happen that like those various considerations will be in tension, right? So it doesn't happen in this case, but one can imagine a situation where on the one hand a given choice leads to radical indeterminism, on the other to avoid this, we would need to choose a kind of maps which identifies empirically equivalent models, and that would be an example of a situation. I don't think it ever happens actually, but in such a situation we would have like different competing reasons for choosing or not choosing a given kind of maps as the proposed like standard of physical equivalence. So those representational considerations do appear in that broader picture. For example, in that issue of empirical equivalence of models, but perhaps not only there.
So I guess the way I see it, I mean, the question of physical equivalence, right, is the question of representation. So I have these two models. Do they represent the same physical situation? That's what it means to be physically equivalent. So how is that question about physical equivalence sort of being settled? Because sorry, this is another old guy thing. All the attempts to do it in a purely formal way just fail miserably, because it's about how how you think the model, the maths latches onto the world, and you have to sort of say something about that. So I assume it's sort of built in there, I guess. But,
yeah, that's right. But like the general problem with theoretical physics is that relating models to what they represent is not straightforward. But one consideration that makes us closer to physical reality is the issue of empirical equivalence, which might also not be so straightforward, but it's easier in the sense that we're relating like the observable consequences of models with what we can observe. And by the way, in what I'm saying, I presuppose that empirical equivalence is not the same as physical equivalence. Like physical equivalence concerns also those not directly observable parts. So I would say like empirical equivalence is one constraint when we are going to establish physical equivalence, but it might not be the only one, and it might not be obvious at a given stage of analyzing a theory what are really empirically, which models should we regard as empirically equivalent and which not. So they are those other various kinds of considerations, such as that issue of radical indeterminism that I analyzed, and potentially some others. Perhaps they could differ from theory to theory. And in that large iterative reasoning, we should take into account all those different pieces of information about a theory that we have, what we know about relating it to experience, what we know from its formal analysis, in particular relative to which kinds of maps it is radically deterministic and relative to which kind of maps it isn't. And like we hope that by taking into account all those various pieces of information and in this iterative way, which means by choosing tentatively some interpretation and seeing what are its consequences and whether we fit and how well they fit to what we know. In this way, we hope to achieve some equilibrium point of interpretative investigations where we will reach an interpretation with which we are happy and which first well in all those different aspects that should be taken into account, both formal and empirical.
Okay, Renate, last question.
Yeah, I don't have a question but a comment. So, yeah, so nothing deep I can add to the content of your talk, but these non-Hausdorff dimensions, they don't appear a lot in physics or in gravity. But there's a person at the Okinawa Institute, I don't know whether you're aware of him and his work, he's called David O'Connell. And he has, for the last few years, he's been studying, Hausdorff geometries motivated by the issue of topology change and motivated by, in a way, the path integral. And this age-old question, should we include, different topologies in the path integral? And if we do, how should we weigh them? So there, of course, people have argued, it's just in two-dimensional point models, what happens, how should we weigh things where, these bad causal points, so this is Salkin et al. But he's looked at a more extended thing with non-Hausdorff and also came up with local models of geometry and how this should be maybe reflected in, terms that should be added in gravitational action to weigh those and then come up with, what is suppressed, what isn't. But it may be worthwhile just looking, at what he's doing. There may be some commonality, some inspiration there, because, it's one of the few people I've heard talk about Hausdorff, but now you're the second person. So maybe have a look at that.
Good. Thank you very much. I didn't know about this person, and what you say sounds very interesting, so I will definitely have a look at this. Thank you.
Okay, please join me in thanking Joanna.